So now let's start talking about double integrals, and we'll talk about some of the practical stuff. So let's start out with the integral of a constant, or the double integral of a constant. And so what we're looking at here is if we think about this theoretically, we've got a region R, and our region R is AB cross CD. And so basically, if we kind of think about that, we're on the XY axis, okay? And so that's like 1, 2, well, whatever. Let's say that this is A to B, and this is then C to D, okay? So what we get is we're going to end up getting a region, and the area of the region, okay? The area of the region is going to be B minus A times D minus C. Okay, if you think about it, that's just like its length times its width. All right, so here's B minus A is that length, and then D minus C is that length right there. Okay, multiply the two of those together, you get the area of the region. Now, if we have what we have here, we kind of imagine that we'll get a figure, and that this figure here has, right, let's say it has a height of m. So there's the height m, little m. And now here's our region, and we know the area of the region is equal to b minus a times d minus c. Then the volume is just going to be, we're basically going to be getting a cube over that region. Okay, so we've got this region, we're going to construct a cube. All right, so there's m. And so that volume is then going to equal m times b minus a times d minus c. Okay? And that's it. So that's actually the whole deal. I mean, so if we're taking the double integral constant, what we're saying is we're saying that the value of the curve is constant. And so that means that essentially we're going to get basically that plane at z equals m. So we got that plane at z equals m, and we're going to find the volume over this region of AB cross CD. Okay, so let's take a look at an example. So if we do that, now let's suppose that f of xy equals 2, and our region is 3 by 5, or 3, 5 cross negative 2, 3. So we've got that. That's the region that we're going to integrate over. And so let's go and find the double integral over r of f of xy dA. So we don't actually need to go out and find that double integral. What we actually have here, again, is we're going to find this volume. So it's going to be 2 times, and this will be 5 minus 3 times 3 minus negative 2. And so this is going to end up equaling 2 times 2 times 5, and that equals 20. And that actually is the value of the double integral. We've actually found the volume of that region. All right, so in this case, we want to be very straightforward. All we're doing is we're actually just finding a volume. Now let's take a look at Fubini's theorem. And Fubini's theorem actually can kind of help us, can kind of come in handy if what we're doing is we're integrating over regions that are, maybe it might be easier to integrate in one direction versus another one. You know, like say we have one complex function of x and the other one's a less complex function of y. Or if, you know, what we want to do is we want to do some proving work. Basically what Fubini says is we've got, suppose that f of xy is a function of two variables that is continuous over a rectangular region, and we have r equal to xy belonging to r squared, or r2, excuse me, x greater than or equal to a, less than or equal to b, y less than or equal to c, less than or equal to d. That's just the same region. That's AB cross CD. And we see for the double integral of f over the region equals an integrated integral. So that's f of xy dA. And what I want you to notice is that we can either c to d dy and then a to b dx, or we can do a to b dx and then c to d dy. And we talked about that a little bit, but that's what Fubini's theorem is stating. And what this says more generally is that it's true if f is bounded on r. Okay, so as long as f is bounded on r, that is that it doesn't go to infinity anywhere, and f is discontinuous only a finite number of continuous curves. And what that means basically is for our purposes, is that f has to be integrable over r. Okay, so there can't be any big holes. A tiny little hole, one hole, fine. Like, 'cause if it goes to infinity somewhere, like at a single point, that's actually okay. Because it's only one point that you've taken out of the volume. But, you know, for our purposes, we're going to be pretty much going to be able to use Fubinis whenever we want to. So, let's take a look at this in action. So let's look at this example. So let's say we want to find the integral from 0 to 2, 0 to 3, 3x squared minus y dy dx. Okay? So we're going to do the dy's first. So that means that our boundary for the y's is 0 to 3. So we're going to treat the x's as if they're constants. Well, if I do that, what we're going to do when we integrate, by the way, in this case, we can't actually factor out the x's, we factor out the y's. We cannot use that single integral version. So we don't want to do that. So let's say, for example, we do this. So now we've got 0 to 2. And so 3x squared is treated as a constant because it has no y's in it. So when we integrate a constant, right? So like, for example, if I had 2 dy, that's just going to end up being 2y, right? 2y plus c. So this now ends up becoming 3x squared y. And then the integral of y is going to be minus y squared over 2. And then dx. Excuse me. And then we'll evaluate that from 0 to 3. Okay? And by the way, remember that these are only y's that we're going to evaluate this for. So, and then this will be dx. So this is going to be equal to the integral from 0 to 2. And then this is going to be now 3x squared times 3 minus 3 squared over 2 minus 3x squared times 0 minus 0 squared over 2. So notice here that all I've done is I've just gone in and I've replaced all my y's with 0 and 3, just like I would do if I were doing an integral. Just like I would be doing if I were doing just a single integral. But in this case, we've got to go in and we've got to treat all of our x's as if they're constants. All right? So there we go. And then this will be finally dx. And so this equals the integral from 0 to 2. And then this is going to be 9x squared minus 9 over 2. And then that'll be all dx because this just becomes 0. All right, that's just a 0. And now all I've got to do is integrate with respect to x. So this ends up equaling 3x cubed minus 9 over 2x evaluated from 0 to 2. So this will become 3 times 2 cubed minus 9 over 2 times 2 minus, and then this is just zeros because those will just zero out. Okay, because they're both going to be evaluated at 0. And so this ends up equaling 3 times 8, that's 24, minus 9, and that equals 15. Awesome. All right, so that gives us an example of how we're going to roll with an iterated integral. What we want to do now is we actually want to demonstrate Fubini's. And so Fubini says, hey, look, I can just switch it around. I can switch around the bounds. And then I'll switch around which variable I'm going to integrate with respect to first, okay? And that should also give me the same answer. So we're going to do 0, 3, 0, 2, 3x squared minus y dx dy. So we've got our example 2 is going to go 0, 3, 0, 2, and this will be 3x squared minus y. And now we're going to do dx dy. So we're going to do x first and then y. So we'll do that first. And so we're going to treat y now as the constant. So again, like if you have the integral of y dx, that's just going to end up giving me yx. Okay? So this will now be the integral from 0 to 3. And then we're going to get x cubed minus yx evaluated from 0 to 2 dy. Plug that in, and we get 0 to 3, and this gives me 8 minus 2y, okay, minus, and then this is going to be 0 cubed minus y times 0, which is just 0 again, and that's now dy. So if you look here, this is just going to give me 8 minus 2y evaluated from 0 to 3, okay, and dy. And now I can just say, okay, well, this is going to give me 8y. This will give me minus y squared. I evaluate this from 0 to 3. This ends up equaling then 24 minus 9 minus 0 minus 0, which 24 minus 9, that's 15. And there we go. See, 15 was the answer to our first question, or to the direction where we did dy first. Now 15 is the value that we get when we put in dx first. And this actually helps us to demonstrate Fubini's and the iterated integral. So let's talk now about the average value of a function. This is an application of doing double integrals, and it's an application of integration. Now let's suppose that I want to find the average of f, and we're working with just a function of a single variable. Recall then that we're going to have that average is going to equal 1 over b minus a. So that's the length of the interval that you're looking at times the integral from a to b of f of x dx. So basically what we do is we're going to take the area of the region and then we'll divide through by essentially its length or its width, if you want to think whatever you want to think about it as, and then that actually ends up giving me the average value, right? It's like, kind of constructing a box over the entire region. To find the average value of a function in two variables, all right, then what we're going to do now is we're going to think about the same thing, except for the fact that we're going to divide through by the area, okay? So before you were dividing through by this length because you're thinking about a two-dimensional figure. Now what you're going to do is you're basically going to like divide out two of the dimensions to be left with that single value for the average. So my f_av here for a function of two variables is going to equal 1 over the area of R times the integral over the region R of f of xy dA. So essentially, this is the exact same process as finding the average value of a function, but instead we're going to divide out by the area and we're going to take the double integral. Okay? So let's take a look at an example. So let's take a look at this question. Let's say, for example, we want to find the average value of f of xy equal to x to the fourth plus 2y cubed on the region R from 1 to 2 cross 2 to 3. So what we'll do first is we'll actually generate an integral. So I'm going to do my y's first. I'll take this, I'll make it 2, 3, and then I'll go 1, 2 being my x's. Then I'll have x to the fourth plus 2y cubed, and then this will be dy dx. That's the order that I placed them in. And then remember that I'm going to have 1 over the area. Well, the area here, will equal, and it'll be b minus a times c minus d. So it's going to be 2 minus 1 times 3 minus 2, which equals 1 times 1 and equals 1. So the area there is 1. So my average value, it turns out, is going to be equal to the double integral because the area of the region is just 1. So this will then equal, we'll do the iterated integral, just give us another example. We're going to get the integral from 1 to 2 of, and remember we're doing this with respect to y, so we're only integrating with respect to y. So this is x to the fourth y plus 2 fourths y to the fourth, evaluated from 2 to 3, and then dx. This will then equal the integral from 1 to 2. We'll plug in our 3 and our 2. We're going to get 3x to the fourth plus, and this is 1/2 3 to the fourth minus 2x to the fourth plus, and this is 1/2 times 2 to the fourth. And then dx. So we'll go in, we'll evaluate that. What that leaves me with is it leaves me with x to the fourth minus 65 over 2. And we're going to take the integral of that from 1 to 2 dx. This will then equal 1/5 x to the fifth minus 65 over 2x from 1 to 2. And so this then equals, and so this is going to be 2 to the fifth over 5 minus 65 over 2 times 2 minus 1 over 5, right? Because it's going to be, or 1 to the fifth over 5 minus 65 over 2 times 1. And then we'll just go in, we'll evaluate that. And when we do, what we end up with is we end up with negative 26 and 3/10. Now remember, we're just going to multiply that by 1 because that actually is the area. So our average value is going to be negative 26 and 3/10, or negative 26.3. All right, and so that essentially, that's just one of the applications that we can use of the double integral, is to find the average value of functions in two variables. So that finishes up double integrals over rectangular regions for us. This is the practical one, a shorter one, but once you've got kind of the theoretical end, it's really nothing too extraordinarily complicated. It can be computationally intensive, and so sometimes it really can be a little tricky and somewhat hard. But the thought or the concept of it is pretty straightforward. Keep one of the variables constant, okay, and then integrate with respect to this second variable, okay? That's it. That's all you're doing. Don't forget that you have these properties of double integrals. I put them up in the notes for you. They actually can also be very handy for you, or very valuable, especially as we do more work with proof and you start seeing things come up inside of the lectures. And also in case you want to simplify the process of finding integrals sometimes, because sometimes using these can actually be really easy. It can make things a lot easier too. All right, so that finishes it up. That finishes up double integrals over rectangular regions.